Assalamualaikum warahmatullahi wabarakatuh. My name is Farika. I'm from Group 1. Along with my friend Shahiran, Ikram, Shahmi, and Irfan, we would like to present about our lab. Now we go to the objective of Lab 1. This experiment identifies how the refrigerant release heat into the coaxial condenser. The enthalpy change is determined by measuring the pressure and temperature at inlet and outlet. It shows how effective the condenser to remove heat, and it contributes to overall performance of heat pump. The second experiment is now focused on the compressor. The compressor work input is calculated by using measured inlet and outlet. With assumption to neglect heat loss, this experiment evaluates compressor efficiency and identify energy losses that affect total power consumption. For the final experiment, we combine system measurement to identify heat pump's COP. The heat output is calculated by using temperature rise and the flow rate of cooling water, while compressor power is measured directly. This provides an overall assessment of heat pump's efficiency and its agreement with theoretical expectation. We go to the procedure of experiment 1, 2, and 3. Firstly, we start and check all equipment and instruments are in proper condition. Secondly, we open the water supply and set cooling water at 1 to 2.5 LPM. And we switch on main power, control panel, and compressor until the temperature and pressure are constant. Then record TT1 and TT2 at desired flow rate. So we change the water flow rate and repeat the experiment. During shutdown procedure, we switch off compressor, control panel, and lastly, the main power. Don't forget to close the water supply and end the experiment.
Next, we move on to the result of experiment 1. As you can see, there are 5 groups here. So our objective is to find out cooling water flow rate and refrigerant inlet temperature or TT1 degree Celsius, pressure bar at PT2. So as you can see, the cooling water flow rate is decreasing as the temperature in the Celsius. But the refrigerant pressure at PT2 is increasing. After we found out the pressure from experiment bar from each group, we can determine the temperature from the table or T saturated in degree Celsius and the temperature from experiment or TT1. So from these two results of temperature, we can find out the phases of each group. If the temperature from an experiment is lower than temperature from the table or T saturated, so they are in compressed liquid phase. Next, our objective is to calculate the delta H equal to Hg minus Hf. So from each group, we have pressure in bar from each group. We can determine the H for gas and H for fluid from each group using the table that provided. So to determine the delta H, Hg minus Hf, and we got the result from each group for delta H.
Okay, for the experiment 2, these are the results that we get from the experiment, where the refrigerant inlet temperature TT1 at group 1, when the cooling water flow rate is 2.5 LPM, the refrigerant inlet temperature is 17.8 degrees Celsius, and the inlet pressure is 3 bar, and then the refrigerant outlet temperature at 49 degrees Celsius, and the refrigerant outlet pressure is 7.9 bar. And then there are group 2, where cooling water flow rate is 2.0, and the inlet temperature is 21.3 degrees Celsius. The inlet pressure is 3.4 bar. Then the outlet temperature 46.6, and refrigerant outlet pressure 8.4 bar. And then there are group 3, where the water flow rate is 1.7 lpm, and the inlet temperature is 16.6, and the inlet pressure 3.4 bar, outlet temperature 50.2 degrees Celsius, and the outlet pressure 8.7 bar. And then at group 4, the water flow rate is 1.5 lpm, the inlet temperature is 15.6 degrees Celsius, and the inlet pressure 3.4 bar, and then refrigerant outlet temperature at 50.1 degrees Celsius, and then the outlet pressure at 8.9 bar. Then lastly is group 5, 1.0 lpm of cooling water flow rate. The inlet temperature is 16.6, and then the inlet pressure is 3.6 bar. And then the outlet temperature is 49.3 degrees Celsius, and then the outlet pressure is 9.7 bar. Okay, then we move on to where we are need to determining the inlet and outlet phase of the refrigerant during the experiment. Okay, then we see here at group 1 where the inlet pressure are 3 bar and the inlet temperature are 17.8 degrees Celsius. Then the inlet phase are superheated vapor where the temperature get from the experiment are greater than T saturated that we get from interpolation at table A12 at superheated refrigerant. And then we also look at the outlet phase where the pressure outlet is 7.9 bar and the temperature is 49 degrees Celsius. It also in superheated vapor phase where the T get from experiment are greater than T saturated. Then we can see here at group number 2 where the inlet is 3.4 bar and the temperature inlet is 21.3 degrees Celsius. It also superheated vapor because the temperature are greater than the T saturated. Then at the outlet also superheated vapor where the temperature are also greater than the T saturated. And we can see through here from group 1 to group 5 also are superheated vapor from inlet and outlet phase because their temperature are greater than T saturated. Okay, so we then move to where we require to find the work input to the compressor. So firstly, before we can find the work input to the compressor, we must find the enthalpy of the inlet, enthalpy of the outlet, and then the mass flow rate of the water cooling first. And then if we get the value, then we can compute all the value to the equation where we can see there uh, at the last side where the W equal to m dot n h2 minus h1. So that's the equation. And then we can see the value at group 1 where the enthalpy inlet is 266.14 and at the outlet enthalpy is 285.86 and the mass flow rate is 0.0417 kilogram per second. And then so when we compute all the value, we must cancel out the unit for enthalpy and the mass flow rate, and we get 0.223 kilojoule per second equal to 0.8223 kilowatt of work into the compressor. So the step also same for the group 2 to 5, where at the group 2 we get 0.4665 kilowatt, and group 3 we get 0.6062 kilowatt, and group 4 we get 0.5795 kilowatt, and for the last group 5 is 0.3161 kilowatt. Okay, so that's all from me.
Lastly, for our experiment for this subject, thermodynamic, is COP determination of the heat pump. So from group 1 until group 5, the cooling water flow rate is decreasing from 2.2 until 1.0. Cooling water inlet temperature TT5 is in average in 26 degrees Celsius. But for cooling water outlet temperature T6, it's increasing from 29.7 until 37.7 from group 1 until group 5. The power input for group 1 is 297, group 2 325, group 3 326, group 4 330, and lastly for group 5 is 340. For discussion, here is our data after we calculate using all the formula, which is Q equal to m dot Cp delta T, Cp equal to 4.18 kilojoule per kilogram degree C. LPM convert to kilogram per second. So from group 1, m dot is 0.0367 kilogram per second, group 2 0.0333 kilogram per second, group 3 0.0283 kilogram per second, group 4 0.0250 kilogram per second, and lastly group 5 0.0167 kilogram per second. For delta T, which is the temperature difference, 3.4 degree C, for group 2 5.7 degree C, group 3 7.6 degree C, group 4 8.3 degree C, and lastly 11.3 degree C. As you can see, the temperature is increasing. Lastly, for Q, group 1 0.522 kilowatt, group 2 0.793 kilowatt, group 3 0.988 kilowatt, group 4 0.867 kilowatt, and lastly group 5 0.788 kilowatt. Then we need to calculate the COP, coefficient of performance of the heat pump. Here is the formula QH over W in, W net. Desired output equal to required output. So for group 1, after we calculate, we got 1.76, group 2 2.44, group 3 2.76, group 4 2.63, and lastly group 5 2.32.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Shamifan bin Sadeh, and I will be presenting about conclusion for experiment 1, 2, and 3. So for conclusion for experiment 1 is when the refrigerant enters the condenser as compressed liquid for all flow rates, it shows that the system is currently operating as a normal operation. For the second one is the higher cooling water flow rate produce a larger enthalpy drop, meaning the system will producing better heat removal. For the third one is lower flow rates cause higher condenser pressure and reduce cooling efficiency. Overall, the experiment confirmed the strong influence of water flow rate on condenser performance and heat pump efficiency. For experiment number 2, when the refrigerant entered and exit the compressor as superheated vapor, it's confirming that the refrigerant are reacting as a correct vapor compression behavior. Compressor work input varied with cooling water flow rates due to change in suction pressure and temperature. The higher water flow generally increase compressor works because of higher pressure ratio. The experiment successfully demonstrated how inlet condition and condenser performance affect compressor energy consumption. Lastly, in experiment 3, we can see that heat output and COP were successfully calculated for all flow rates. And we can see that very high flow rates reduce the temperature rise, thus lowering heat output. For very low flow rate, increased temperature rise but reduce mass flow, thus limiting heat transfer. The experiment confirmed the optimal COP requires for a balanced cooling water flow rate.